Alright, in this video we're going to be looking at infinite series. So let's give an example of what an infinite series looks like. So an infinite series will have a starting index. Usually it's n equals 1, sometimes it's n equals 0 or n equals 2. And then it's an infinite series, so the upper bound is going to be infinity. You're going to have some sort of seed sequence a sub n. And that's going to just simply be a1 plus a2 plus a3 plus all the way out to a sub n, and we just keep on going. So to give you a more concrete example of what an infinite series could look like, let's look at the sum n equals 1 to infinity of 1/2 raised to the n minus 1 power. So terms in this series would look like 1/2 to the 1 minus 1 plus 1/2 to the 2 minus 1 plus 1/2 to the 3 minus 1 plus dot 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 plus 1/2 to the n minus 1, and that's going to keep going. So simplifying that, that's going to be 1/2 to the 0, which is 1, plus 1/2 plus 1/2 squared, which is 1/4, plus all the way out to 1/2 to the n minus 1, and then it keeps on going. Okay, the a sub n, the sequence a sub n, is the, I like to call it the seed sequence. I don't know if that's the official term, but I call it the seed sequence. And when we're talking about an infinite series, we're interested in sometimes what the sum is, sometimes whether the series converges or diverges. So those are certainly things we're interested in. And so to get at what that sum is, we look at what's called the partial sums. So the first partial sum is simply the first term. The second partial sum is the sum of the first two terms. The third partial sum is just the sum of the first three terms, all the way out to the nth, which is the partial sum of the first n terms. So for example over here, a sub n would be 1/2 raised to the n minus 1. So the first partial sum would simply be 1, and the second partial sum would be 1 plus 1/2, which is 3/2. And the third partial sum is going to be 1 plus 1/2 plus 1/4. So the first two added up to 3/2 plus 1/4, and that's going to be 7/4. And we want to know, maybe there's a way we could come up with a formula for the nth term, or the nth partial sum. If we could do that, then we might be able to talk about the limit of the series, or what the infinite series is. So we look at the limit of the partial sum. And so here's what s of n looks like. 1 plus 1/2 plus 1/4, all the way out to 1/2 to the n minus 1. So is there a way to describe that? And the answer is yes. But before we get into that, I'm going to talk about the convergence. If the partial sum s of n converges, then the infinite series converges. If the partial sum, the limit of the partial sum diverges, then the series diverges. Okay. So if the limit as n goes to infinity of the partial sum s of n is equal to s, we say that the sum n equals 1 to infinity of a sub n, that sum is equal to s. Okay, and so that's what we mean by the series converges, is it's the limit of the partial sums converges. If the limit of the partial sums diverges, then we say that the infinite series diverges. Okay, so now let's go and look at, is there a formula for 1 plus 1/2 plus 1/4 all the way out to 1 to the 2n minus 1? So we're going to make the claim that for x not equal to 0 and 1 plus x squared plus all the way out to x to the n can be written as 1 minus x to the n plus 1 over 1 minus x. Okay, so we're going to just go through and we're going to look at, well, let's say that n is equal to 0. So we're only finding 1. So is 1 equal to 1 minus x to the 0 plus 1 all over 1 minus x? And so that is 1 minus x over 1 minus x. That's 1. So this formula is true for n equals 1. Now what about n equals 1? So that'd be 1 plus x to the first power. So 1 minus x to the 1 plus 1 all over 1 minus x. So let's see if this is true. So that's 1 minus x squared over 1 minus x, which is 1 minus x times 1 plus x, difference of squares, all over 1 minus x, and so that is 1 plus x. And so this formula seems to be working for n equals 0 and n equals 1. And then this is kind of a induction proof sketch. So the next thing is called the induction hypothesis, and we suppose for some k less than n that the formula is true, namely that 1 plus x squared plus all the way out to x to the, sorry, that should be x to the k. That's going to be equal to 1 minus x to the, I did it again here, didn't I? X to the k plus 1 all over 1 minus x. So that's our induction hypothesis. Now we're going to go ahead and consider the next term in the sequence would be the x to the k plus 1. And so we're going to add that in. So 1 plus x squared all the way out to x to the k and x to the k plus 1. Sorry, this should be a k here. All right. So the first k terms, or actually it's going to be k plus 1 terms, because 1 plus x squared all the way out to x to the k, that's going to be k plus 1 terms. Anyways, that is our induction hypothesis. We're going to assume that that is 1 minus x to the k plus 1 all over 1 minus x. And then we're going to add to it the x to the k plus 1. So we're going to get a common denominator, and then we're going to multiply by 1 minus x over 1 minus x. So we have 1 minus x to the k plus 1, and then x to the k plus 1 times 1 is x to the k plus 1, and x to the k plus 1 times negative x would be negative x to the k plus 2, all over 1 minus x. And that's going to be 1 minus x to the k plus 1, and then plus 1, so it fits the form, all over 1 minus x. And so that's a sketch of an induction proof. Maybe you've seen it in pre-calculus, maybe you've seen it in some other math, but we won't do too much with induction. But you might have seen it in Cal 1, where we prove some of those sum formulas, like the sum I equals 1 to n of I, for example, was n plus 1 all over 2. So maybe you remember some formulas like that. And so that can be proved using mathematical induction. Okay, so we're getting closer to having this formula for the partial sum. Now, the next thing I just want to point out is how the series, how we can start it at 0, and how we can start it at 1, how we can start it at 2, and how we can start it at 3. And it's going to end up giving us the same series, it just looks different. So I want to compare the sum n equals 0 to infinity of 1 over 2 to the n with the sum n equals 1 to infinity of 1 over 2 to the n minus 1, and compare that with the sum n equals 2 to infinity of 1 over 2 to the n minus 2, and the sum n equals 3 to infinity of 1 over 2 to the n minus 3. Now all of these are actually going to end up being the same. Each one of the formulas looks a little bit different, but with a series, you can start it out wherever you want. Typically, we start it at 0 and 1. Later on, there'll be some examples where we might want to start it at 2 or 3. And you could certainly start it with -1 and -2, but I don't see that happening too much. Usually it's 0 and 1. Okay, so we're just going to write out a few terms of the series. So that's going to be 1 over 2 to the 0, plus 1 over 2 to the first, plus 1 over 2 to the second, all the way out to 1 over 2 to the n minus 1, and then it's going to keep going. Now 1 over 2 to the n minus 1, that's actually the nth term because we started at 0. So we start at 0 all the way out to the n minus 1 term, that's n. Okay. All right, now the next series we're going to start at 1, so it's going to be 1 over 2 to the 1 minus 1 plus 1 over 2 to the 2 minus 1 plus 1 over 2, 1 over 2 to the 3 minus 1, all the way out to 1 over 2 to the n minus 1, etc. Okay. Now the next series starts at 2, so 1 over 2 to the 2 minus 2 plus 1 over 2 to the 3 minus, sorry about that, that should be also a minus 2. 3 minus 2 plus 1 over 2 to the 4 minus, and that should also be 2. Okay, plus all the way out to 1 over 2 to the n plus 1 minus 2. So to go from 2 to n plus 1, that's going to be n terms. All right, and then the last series we're going to look at is the sum n equals 3 to infinity of 1 over 2 to the n minus 3. So 1 over 2 to the 3 minus 3 plus 1 over 2 to the 4 minus 3. Oh, looks like I did it again here, huh? Okay, so we got the index mixed up there. Not the index, but the what we're subtracting there. 1 over 2 to the 5, and it should say minus 3 there. Excuse me. Okay, all the way out to 1 over 2 to the n plus 2 minus 3. So from the third term to the n plus 2 term, that's actually going to be n terms there. All right, and so if we simplify this down, the first series is 1 plus 1/2 plus 1/4 plus all the way out to 1 over 2 to the n minus 1, etc. The second series ends up being exactly the same here as well. And so does the third one, and the fourth one will all end up being the same. So you might see your series started at different indices, and so just know that oftentimes equivalent series will start at different indices. Okay, so let's look at this sum of 1 over 2 to the n, and we'll start it at 0, and we're going to find the limit of the partial sums, okay? So the sum n equals 0 to infinity of 1 over 2 to the n, so that's 1 plus 1/2 plus 1/4 plus 1 over 2 to the n minus 1, etc. That's what that series is. So S of n, that's going to be the first n terms. So we are starting at 0, so that's going to be 1 plus 1/2 plus 1/4, all the way out to 1 over 2 to the n minus 1. So from 0 to n minus 1, that's actually n terms. So it's a little bit, you got to be a little bit careful there. Now we're going to use the formula 1 plus x squared plus blah 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 1 over x to the n. We're going to use a modification of that. That is 1 minus x to the n plus 1 all over 1 minus x. Okay, so instead of x, we're going to have 1/2, and instead of n, we're going to have n minus 1 in place there. So let's go ahead and use that here. So we have 1 minus 1/2 to the n minus 1 plus 1 all over 1 minus 1/2. And that's going to be 1 minus 1/2 to the nth power all over 1/2. So we're dividing by a fraction, so we'll go ahead and take the reciprocal. And so that's what our partial sum is. And now we have something we can take the limit of, so we're going to take the limit of that partial sum. We have a specific formula for that. Okay, and then we're talking about an exponential function, and the base is 1/2, so we're going to have exponential decay. And so as n goes to infinity, the function is going to go to 0. The 1/2 to the n is going to go to 0, or 1/2 to the x if we're going to consider a function. 1/2 to the n can be coupled with 1/2 to the x, and so they're both going to do the same thing. So this limit becomes 2 times 1 minus 0, and so the sum there is 2. The limit of the sum is 2, and so that's what we call the infinite series. The infinite series has a sum of 2. Okay. Now let's say that instead of n equals 0 to infinity, we wanted to do the same thing, but we started at 1 instead. So the partial sum would be 1 plus 1/2 plus 1/4 plus all the way out to the nth term would be just an n, so 1 over 2 to the n minus 1. And so it's going to work out exactly the same as the previous one there. And so we just got to be a little bit careful with the index. Okay. And so our partial sum is 2 times 1 minus 1/2 to the n. So the sum n equals 1 to infinity of 1 over 2 to the n is equal to the limit of the partial sums. And the limit of that partial sum we found just a moment ago. The limit as n goes to infinity of 2 times the quantity minus 2 times the quantity 1 minus 1/2 to the n. That was going to be equal to 2. Okay. All right. So one other little item here. This is called a geometric series. So maybe give you a little bit of geometric representation. Okay. So there is 2 squares. They're empty right now, so we have 0. There's 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and we could keep going, plus 1 over 32, etc. And so if we continue this process, eventually we're going to have basically 2 filled in squares, so we could say that the area of those the filled in squares there is going to be 2, and so we'd say that that area is 2, where it converges to 2. Okay. All right, so go ahead and check out the next video, and we'll see you next time.